Can you answer this quiz question? Which ports in this topology are blocking? If you need some time, please pause the video at this point and see if you can answer this question. We've got 5 switches in this topology. Which ports are blocked by spanning tree? Okay, so let's see if we can answer the question practically. I've built this topology in GNS3. I've configured the switch priorities and the switch MAC addresses. Now in spanning tree, the first thing you need to determine is the root switch. Which switch is the root switch? That will affect which ports are blocked in spanning tree. Now first, a bit of history. Spanning tree was developed to stop loops originally in transparent bridged networks. If you remember, the predecessor or the ancestor, if you like, to switches were bridges. Bridges, or what are called transparent bridges, flood unknown unicast traffic, broadcast traffic, and multicast traffic. Layer 2 switches do the same thing. So switches still act like bridges of years ago. They just do things quicker or faster. So if you have problems in a bridge network, you would have the same problems in a switched network. They would just happen more quickly. Switches use ASICs or application-specific integrated circuits to forward traffic very quickly using hardware, whereas bridges used to do things in software. Now, why is that important? In a transparent switched network, which we have today, loops are a problem. As an example, if a PC was connected to the switch and sent traffic to the switch, and let's say it's a broadcast frame, and it arrived on, let's say, port gigabit 04, not shown in this diagram, but let's assume that a PC sent traffic to the switch would flood the broadcast out of all ports. The broadcast that went out of this port would be flooded by this switch, which would be flooded by this switch, and in other words, a single broadcast now comes back to the switch on 2 ports. But in addition, that single broadcast is flooded by switch 3 out of both these ports. It's then flooded by this switch out of both these ports. It then arrives as multiple broadcasts on gigabit 02 back on switch 2. So switch 2 received a single broadcast on gigabit 04. That's now been flooded through the network, and multiple broadcasts are now received by switch 2. That process will continue. We'll have a loop here in the network. We also have a loop here, we have a loop here, and we have other loops, which essentially can result in a broadcast storm and can bring down the network. Spanning tree needs to block ports in the network to ensure that there are no loops in a transparent bridged or transparent switched network as we have today. So again, the first step is to determine the root switch in the topology. Which switch is the root switch? That's based on the bridge ID, which consists of the switch priority and the switch MAC address. The lowest priority wins. If the priorities are equal, then a tiebreaker is done based on lowest MAC address. So in this topology, this switch, switch 2, switch 4, and switch 5 have the lowest priorities. So we need to determine the root switch or root bridge based on the lowest MAC address. This MAC address is higher than this MAC address, which is higher than this MAC address. So switch 2 will be the root switch in this topology. So I'll write root here to denote this as the root switch. I'll change the text color to, let's say, green, so that we can see that this is the root switch. So root switch is that. The next step in spanning tree is to determine the root ports. All switches which are not the root switch have a root port, which is their best port to use to get back to the root switch. Now, that's based on path cost. Each switch will determine its route based on the path cost, in other words, the lowest path cost to get back to the route. If I was driving from San Francisco to Los Angeles, I probably wouldn't drive via New York. It's a longer path. I'd drive directly from San Francisco to Los Angeles. So the same principle applies here. Notice all these links have the same speed, so they will individually have the same path cost. Now the path cost of these links is 4 using the current version of spanning tree. I don't want to show you the show commands yet because it will give away the answer. So let's see if we can work it out manually, and then I'll show you the answers using show commands. Basically, his best path is this link, cost of 4, rather than going this way, which is a cost of 4, and then round this way, which will have a total cost of 8, or going right round, which will have a cost of 4 plus 4 plus 4 plus 4. So from his point of view, best path to get to the root bridge is via gigabit 00. So this will be the switch's root port. Now what about switch 3? It can either go this way. That's got a path cost of 4. This is a path cost of 4, so going that way is 8. It's quicker to go using one of these links. Now, this switch can't use path cost to determine which port to use to get to the root switch. Path cost of both these links is the same. So we need something as a tiebreaker between those two ports. The way spanning tree does that is based on neighbor bridge ID. Neighbor with the lowest bridge ID will win. That doesn't work in this example because both of these links are connected to the same neighbor switch. In other words, switch 2. The next decision is based on priority. Lowest priority wins. So what are the priorities of these two links? By default, the priority is 128. So if we look at switch 2, we can see the priority of the links by typing show spanning tree. So notice gigabit 03, gigabit 01, this is on switch 2 again. These interfaces have a priority of 128. Notice priority over there, 128 on both of these links. So priority can't be used as the tiebreaker. So the next decision criteria is based on interface number. The lowest interface number wins. So gigabit 03, this interface has an interface number of 4 in the output here. This interface, gigabit 01, has an interface number of 2. This is a lower interface than this interface. So this interface will be used as the best path to the root bridge. So on the other side of the link, that's gigabit 01. So if I duplicate this, this is going to be the root port to use to get to switch 2. And let's verify that. So on switch 3, here's switch 3, show spanning tree. Notice the root port is gigabit 01 in this output. So this interface is the root port. It's the best port to use to get to the root switch. So that's correct per our calculations. Now one thing I'll point out here based on feedback that I've been given is on switch 2, if I went on to gigabit 03, notice the current priority is 128. Switch 3 currently has gigabit 01 as the root port. So what I'm going to do on this interface is type spanning tree, various options here, but let's type port priority, and I'll make this priority 64. Needs to be in increments of 32. So I've lowered the priority of this interface. Previously, switch 3 had its root port set to gigabit 01. Type show spanning tree again. Notice root port is now gigabit 03. The root port has moved based on the priority. So the priority of the neighboring switch or upstream switch, in other words, the switch closer to the root switch, determines the root port of the switch. So notice the root port is now changed to gigabit 03. That port is now forwarding, and gigabit 01 is now blocking. If I set the priority back to the default, so notice show spanning tree, priority is back to 128. what we should notice is the root port switches back again. So currently, gigabit 03 is the root port, but after a while, as you can see there, the port has transitioned to a blocking port. This port is back to being the root port in the topology. So the neighboring switch priority or neighboring switch port number determines the root port of the switch. Now on switch 4, this is fairly easy. The path cost here is 4. If we went this way, it would be 4 plus 4 plus 4, which is 12. So this is going to be the root port. That's a simple calculation. What about on switch 5? Notice path cost here is 4 plus 4, which is 8. Path cost using either of these links is 4. Either of these links is 4, so that's also 8. You can't use the path cost as the determining factor, so we need to use something else. And again, the neighboring bridge ID determines which port is the root port. This switch's priority is lower than this switch's priority, so one of these two ports is going to be the root port. And then we look again at the priority and the port number. The lowest port number wins, so I would say that this port is going to be the root port, but let's prove that. So here's switch 5. On switch 5, show spanning tree. Notice gigabit 01 is the root port. So we've worked out the root switch, we've worked out the root ports. The next decision is to determine designated ports. That's done per interface or per link or per segment. So this is a physical link, that's a segment. This is a separate physical link, that's another segment. So on a per segment basis, we need to work out designated ports. Designated ports are the best ports to use to get to the root bridge when you're on that segment. Now all ports on the root bridge are designated ports. You can't get closer to the root bridge than the root bridge itself. So you can immediately say that all ports on the root bridge are designated ports. Think about it this way. If I was sending traffic to the root switch on this link, the best way to get to the root switch is via this interface. And something I like to use is imagine that you had a PC on that link. This PC doesn't exist, but for the moment, imagine that I had a PC in the middle of this link, which is the best way to get to the root bridge on this link. It's going to be easier to go this way than it is to go right round. So this is a better path than going round. But you can immediately just say that all ports connected to the root bridge are designated ports. Once again, if I had a PC in the middle of this link, it would make more sense to go this way to get to the root bridge than to go right round. Okay, so that's simple, but what about these links? Again, just imagine that you put a PC in the middle. Is it easier to go this way? Path cost is 4, so that's 4 plus, let's say, half, 2, 6. So 4 plus 2 is 6 to go left. To go right would be 2 plus 4 plus 4, so that would be 10. It's going to be quicker to go left rather than right. So these would be designated ports. On these links, is it better to go this way or is it better to go this way? Cost here is, let's say, 2 for half a link, plus 2 is a cost of 6. This way would be 2 plus 4 plus 4, that would be 10. It's going to be quicker or better to go this way. So these are designated ports on those segments. Now here's an interesting one. Is it better to go this way or is it better to go this way? Notice this has a cost of 2, so half of the link. This has a cost of 4, so that's 6. This has a cost of 2. Both of these have a cost of 4, so it's also 6. So we can't use path cost as the determining factor for this segment or for this link. Remember, the analogy is this PC is in the middle of the link. It doesn't exist. It's just a way to work it out. So going left is 6, going right is 6, you can't use path cost as the determining factor. We have to look at the neighbor bridge ID. Neighbor bridge ID here is 32768. This one is 16384. This has a lower bridge ID. This number is higher than this number. So the designated port is going to be this one, not this one. This has a lower priority once again than this switch. Switch 3 is going to be the switch used to get to the root bridge, so this will be the designated port once again. So I can delete my PC because I don't need it anymore. I've looked at every segment and got designated ports. So again, if you're using common spanning tree or the old version of spanning tree, you choose one root switch per topology. If you're using per VLAN spanning tree, you choose one root switch per VLAN. So in this example, let's assume we're using VLAN 1. This would be the root switch for VLAN 1. Then per switch that's not the root switch, we choose one root port for that VLAN. So for VLAN 1, switch 4 has this as its root port. Switch 1 has this as its root port. Switch 3 has this as its root port. Switch 5 has this as its root port. And then on a per segment basis, we need to choose a designated port. So on every link or every segment, we need to choose a designated port. We've done that now. So all other ports get blocked. Now again, this can be per VLAN. If you're using per VLAN spanning tree, you can change which ports become the root ports, designated ports, and so forth on a per VLAN basis. But based on what we've done here, assuming only one VLAN, these ports will get blocked. And let's see if we got it right. So let's start with switch 1. Switch 1. You can see the answer there. Gigabit 01 is an alternate port. It's blocking. So that's a blocking port using Cisco terminology. So again, there's the output. That port is blocking. What about switch 3? On switch 3, show spanning tree. Gigabit 03 is blocking. That's known as an alternate port. Just to reiterate, Gigabit 00 is a designated port. We can see that there. Gigabit 01 is the root port. That's correct. Both Gigabit 02 and Gigabit 10 are designated ports. The blocking port is Gigabit 03, as we can see over here. So we've worked that out properly. Let's look at switch 5. Switch 5, show spanning tree again. Gigabit 00 is a designated port that's not used in the topology. Gigabit 01 is the root port. Gigabit 02, 03, and 10 are blocking ports. Now this is the problem with common spanning tree, or the old version of spanning tree. This switch has 4 links, but only one of them is being used. So what you can do with per VLAN spanning tree, or rapid per VLAN spanning tree, or multiple instance spanning tree, is do a bit of a load balancing or load sharing, because it's not pure load balancing. You could make this switch the route for some VLANs and this switch the route for other VLANs, so that some traffic is sent across this link for, let's say, odd VLANs, and other traffic is sent across this link for even VLANs. You can even do more work and then get load balancing across multiple links, like both these links or both of these links. Again, it's not load balancing as in per packet load balancing, it's load sharing, because as an example, you could have a VLAN for phones where some traffic is sent, but then a data VLAN where even more traffic is sent. So it's not equal load balancing. You're kind of sharing the links between different VLANs. This is not a great design. This design or this lab is just used to teach you how to work out which ports are root ports, designated ports, and blocking ports. Okay, so there you go. We've worked it out. That's the answer to this quiz question. I hope you enjoyed this video. If you did, please like it. Please, if you don't mind, subscribe to my YouTube channel if you haven't already. That really helps me. I'm David Bombal. Want to wish you all the very best.